let's do one example of computing the expectation of a given random variable by the means of the conditional expectation. Okay. So this example is an interesting example which talks about a store, actually a superstore. Maybe you can assume that you are talking about a superstore which kind of sells the exotic shops. Okay. And suppose that we know that there are some average number of people who visit that shop every day, okay, and there is an average amount of money that they spend in that shop, actually. Okay, so let's think about it. So imagine this is a superstore. Okay, so we assume that this is a superstore that sells what do you call an exotic shop, actually. Okay. Now, if n represents the number of people that visit this shop in a day, okay, assume that it is known that this random variable is normally distributed with average 50 and some standard deviation, actually, which we don't need, actually, in doing these calculations. We just need averages. So there are on average 50 people which visit this shop, and the number of people is normally distributed, actually. So in other words, first less number of people visit in the day, and then the number of constable increases and then decreases, actually. So in fact it makes the bell curves. Anyway, so n represents the number of people that visit that shop on that day. And suppose that xi represents the amount that ith customer, okay, ith customer spends in a store on a given day, okay, on a given day. So xi is some amount of the money, okay, that they that they spend in their store on a given day. Okay, so there are total n people. Okay, so say on average that there are n people which visit the shop in a given day, and xi kind of represents the amount that ith customer spend on in a given day. So you can say that basically there are n amounts. So in other words, x1, x2. So there will be n random variables. Okay, xn. So x1 is the amount. So again, so since there are n people, okay, n random people that visit the store on a given day, then x1 is the amount that the first person spent in their store on a given day. x2 represents the amount that the second person spent on that in that store in a given day. xn represents the nth person that spent that is some amount on in their store on that given day, actually. Okay, so all these numbers. So what we know about these spendings, that it is given that these all are independent. Okay, we don't know about their distributions. They are independent. everyone spends some amount, say it's given that $8 on that day actually. Okay, so what does this $8 means? That each customer on average spends $8 in their store when he or she visits the store actually. Okay, so this is the given piece of information. It is also given that the number of people n, okay, and money that those people spend, okay, in other words, these xi, that is this x1 up to xn, are independent. Okay, independent. The question is, what is the average expected amount of the money that is spent in a store on a given day actually? Okay, what is, so the question is, what is the amount of money that all these n customers will spend, okay, together in the shop on a given day? Money. What is the average? What is the average amount of the money that was that will be that happen, whatever, spent on in a day. So this is the question that we will have to answer. So let me give you a bit of details again. So imagine you have some superstore, and n represents the number of the people that visit that superstore or that enter into that superstore on a given day. Okay, so it is known that this n is normally distributed with average 50 actually. So in other words, on average there are 50 people in a given day that visit what do you call the superstore actually. And say xi represents the amount that ith customer spends in the store on that given day actually. Okay, so since there are n customers, which is a random quantity which enters into the store, okay, so there will be x1, x2, xn is the money that these n customers will spend on that given day in the store actually. Okay, suppose that we know about these spending, that all these spendings are independent of each other, everyone spends on its own actually. Okay, and the average spending that a person usually that a person does in the superstore is say $8 actually. Okay, so on average, when a person enters into the superstore, on average he spends or she spends $8 at least. Okay, now it is also known that the number of people and the money that they spend in the store, number of people that visits the superstore on a given day, and the money that they spend on in their store on that given day, they are independent of each other. So these random variables are independent of each other. The question is, what is the net amount of spending, okay, in the store on a given day? There are 50 people, for example, visiting the shop or the store on that given day. So the average spending, the average earnings of this store must be 50 times $8 actually, 50 times $8. So this must be the money. So let's see that where our intuition is correct or not actually. Okay. Now, what we would like to do, okay, in this example is obviously we would like to compute that what is the net worth, the net spending done by these n people in the superstore on a given day. So how can I write the net spending? So just sum these spendings actually. So expectation of I equal to 1 to capital N xi, given that there are n people, say n equal to small n people that have visited the store on that given day actually. So this is the average that we will like to calculate. So what would be the net spending by the customers on that given day in the shop, on a given day in the shop, given that n people, the small n people have visited what do you call the shop actually. Okay, so let's calculate this expectation. Now this expectation can, oh sorry, I need to compute expectation of this sum. So what I would like to compute, what would be, so if this is representing the spendings by each customer on what do you call in the superstore on a given day, then we are interested in what is the average spending, what is the average net spending that will occur or that will be done by the customers on a given day actually. Now this expectation can be written as the expectation of, so if I treat this as x, okay, if I treat this as x, okay, then the expectation of this can be treated as the expectation of I equal to 1 to n xi given n equal to n. Okay? So this is what the expectation would be. So it's like expectation of x is equal to expectation of expectation x given y. In other words, what would be the net expectation, expected spendings by the customer? So this is equal to that what is the on average, what is the average of the average spendings done by the customers, okay, given that there are small n people who have visited what do you call the visited the store actually. So I can write this conditional expectation as that actually. Now what would be this? So if this is the case, then I can say that the expectation of the sum is the sum of expectation. So I can write this as this is equal to sum that I goes I equal to 1 to n xr, okay, xi expectation of xi given n equal to nn. Okay, this is what it is going to be. So the expectation of conditional expectation of a sum is the sum of the conditional expectation actually. So we know this. Now what we know about these expectations, I know that these spendings and n are independent of each other actually. Okay, so these spendings and n are independent of each other. In other words, the spending does not depend on, and it makes sense actually, the spending, the amount of the spend that you're gonna spend in a superstore, you don't ever consider that, okay, how many people have visited the superstore, based on that information I consider that, okay, I must spend this or that actually. Okay, you don't care that how many people have visited previously the store actually. Okay, so it makes sense. It's a reasonable assumption actually. So the expectation of the spending that will be done by the ith person, given that the total n people have visited, so these two are independent, so this expectation would be equal to, what do you call, sum of I equal to 1 to n expectation of xi. This is what you're going to get at. So expectation of, so this expectation is expectation of sum of the I equal to say 1 to small n, 1 to small n expectation of xi. Now this expectation of xi is a fixed number, which is $8 actually. And it's not necessary that it should be $8. You can keep it as, for example, mu first and then substitute $8 actually. So this is fixed actually. So you're going to have expectation of, say, sum of I equal to 1 to n, expectation of xi, let's call it, for example, mu, okay, where mu is $8. So this is same as summing this number and mu, what do you call, n times, so you're going to get n mu, and this n, okay, this n is really, what do you call, capital N. I can replace this n by capital N. This could be any number times, what do you call, mu. So expectation of n times mu, so the mu is a number. Mu is a number, so this is same as mu times expectation of n. Okay, so what we calculated, the expected sum of the net spending by all customers in a given day is equal to mu times expectation of n. Now we know about expected value of the random variable n actually. Okay, we know about the expected value of the random variable n, that it is 50. So this is, so the mu is 8 and expected value of n is 50. So it's going to be $400 actually. So the net spendings that will be done by, for example, the total number of people in a given day is going to be the $400. Okay, provided that the average, on average, 40 people visit the store, and on average everyone makes $8 actually. By the way, like these numbers are generic. It's not necessary that mu should be $8. Expected value of n could be some other value as well. So maybe if you are talking about a huge store in which the thousands of the people visit on a given day, and they spend, say, a lot of money in a given, for example, day on, everyone spends, for example, a reasonable amount of money in the store, then this number is going to become big actually. Okay, so I hope this is making sense to you. I hope you also got this point actually, that this sum is going to be n mu, and the n is basically capital N. So I can replace also this by capital N actually. Okay, so this n. So what I'm saying, that this small n is not a fixed quantity, so it's like a random quantity. So the n, this is the quantity that this capital N takes. So therefore I replaced n by capital N, and hence I got this result. So I hope you got some idea that how we can compute, for example, the expectation through the conditional expectation. So this is same as, I mean, if you have seen, for example, the version of result, for example, the law of total probability. Okay, so in the law of total probability, you compute the probability of a given event by in the terms of what you call the conditional expectations actually. Okay, in the terms of, or in the terms of the conditional probabilities. So this computing the expectation through the conditional expectation is really analog to that actually. Okay, even we can deduce that result from what do you call this given result as well actually. Anyway, so I hope you got some sense that this formula for the expectation, computing the expectation through the conditional expectation, is very much analog to law of the total probability actually. Okay, so the law of, so it's like law of, it's analog to law of total probability. So I hope this is making a bit of sense to you. So now let's move to the next topic. And the next topic really is to compute the conditional variance actually. So if you have conditional expectations, the question is, can we talk about the conditional variances? And the answer is that it's not difficult to talk about the conditional variances. Okay, so the conditional variance, we will not get into the calculation of it, do it yourself. Conditional variance is what? So first of all, I would suggest that if I say you to define the conditional variance for yourself, okay, just pause the video for a moment and think about yourself. Try to propose a definition for the conditional variance actually, okay, based on your experience actually, that okay, if you know the expectations, you know how to compute the variances through expectations actually. The question is, can you guess the formula similarly where computing the variances through expectations actually? The answer is that think for a moment, pause the video, think for a moment, and write the formula and see that whether it matches with your intuition or not. Okay, so I hope that you have tried it. And so how we define the variance of a random variable x given y? So we define the variance of the random variable x given y as the expectation, okay, the conditional expectation of x. Okay, so there we say that, so in simple variance we say that by definition you say that how much x variates from its expectation, its square and expectation. Okay. So similarly, how much x variates from its expectation or something else. So I hope you have guessed it that this is going to be the conditional expectation. Okay. Okay. And it's square. So the expectation of x minus conditional expectation, it's a square. We are not done, given y. Given y. So this is important actually. Okay. In other words, on average, if you know y, on average, how much x is variating from the conditional expectation actually. So this is what should be the definition of the variance of x and y. Okay. Now, one little exercise for you is to show that the variance. One little exercise for you is to show that the variance of x given y. Okay, maybe two identities. Variance of x given y is the expectation of, as per we get the expectation of x square given y minus expectation of x given y square. Okay, so it's very much analog to our, what do you call, intuition. Now, as we say that if as the conditional expectation is a random variable, then variance of x given y is also random variable. Why? Because this is a random quantity, that's a random variable with respect to y, okay? And this is also a conditional expectation, so this is random variable. And the variance of x given y is the difference of these two random variables, okay? Is the difference of these two random variables. Now, if variance of x and y is, what do you call, if the variance of x and y is a random variable, you can ask the question, okay, what is the expected value of this random variable? Or what is the variance of this random variable actually? Okay, so we can answer this question actually, that the expected value of the variance of x given y basically equals to expectation of x square minus expectation of x given y square. Okay, so this is going to be the expectation of it. You can see it immediately follows from this formula. So if you apply expectation here, it's equal to the expectation of this quantity minus expectation of this. But the expectation of some